Hi everyone. In today's lecture, we're going to discuss the Fourier transforming property of a lens and some of its applications. We will consider the system shown here. So in the system, we have a single lens which has focal length f, and we consider two planes. This source plane has a distance of f to the lens, and we consider the another plane, a second plane that is also that also has distance f to the lens. And we want to basically understand the relation of the wave field we have in this plane to the wave field we have in the source plane. We're not going to make the derivation for this relationship. This derivation is in your book as well as in the shared notes. We will just state this important relationship, which is given mathematically here. Okay, so basically what we have in this focal plane is the Fourier transform of the object in this plane. Okay, so Ixy in this plane is simply the Fourier transform S, Fourier transform of the object with some scaling. And the scale here is lambda times f. Okay, this is an important relationship. It simply tells us that we can compute Fourier transform of an object by simply replacing a lens in a 2f distance in the middle. If we put a lens in the middle of a 2f distance, then we can compute a Fourier transform. So we can move to the frequency domain or get the frequency domain representation of the signal, the input signal. One important remark here, when we write this relationship, Fourier transform relationship, we're ignoring the finite aperture of the lens. We're assuming that the lens here has an infinite aperture. But in the practical case that the lens has a finite aperture, there is going to be additional distortion on this Fourier transform, additional convolution effect or a blurring effect on this Fourier transform. So you should also keep that in your mind, okay? This picture kind of summarizes what we learned about lenses. So the first thing we learned about lenses, which was something we already knew from high school, is if the imaging condition or if the lens law is satisfied, which means 1 over di plus 1 over ds is equal to 1 over f. In that case, a lens will form an image, okay? Either when we have a coherent illumination or when we have an incoherent illumination. So if we consider a lens here, lens is here, and if this is our source plane at distance ds from the lens, and if this is our image plane at distance di from the lens, that means, for example, if we move ds to infinity, that means if you move our source very far away from our lens, then our image plane will appear at distance f, or we are going to have the image at the focal length or at the focal distance of the lens. We can also look at this result by by using the Fourier transforming property of a lens. And also the Fraunhofer propagation principle. So let's do that. Let's consider that this image plane is in the infinity, in the minus infinity. Then as this wave arrives at distance f from the lens, it's gonna have propagation Fraunhofer propagation model. And we can say that we're going to basically see the Fourier transform of the source in this plane, because the object was at infinity. And here we have the Fourier transform of the source, and we know that from the Fourier transforming property in this 2F system, we're going to get another Fourier transform. So the first Fourier transform was due to Fraunhofer propagation from infinity to this distance. And then we have a second Fourier transform due to the Fourier transform property of the 2F system. And that means we're going to have Fourier transform of the Fourier transform of the image, of the source, which is going to be just the inverted source with some scale. Okay, so we're going to see the image of the source in this plane just as we expect. Okay, as we make this go to infinity, we were expecting to see the image at the focal distance of the lens, and we can also understand this by using the Fraunhofer propagation and then the Fourier transform property of the 2F system as well. Okay, so this was just to synthesize the three property that we learned about wave propagation. Now let's discuss one application of this Fourier transforming property. How can we use that in the applications? Of course, a simple application for Fourier transforming is filtering. So we can filter an image as the way we want by using the 2F system. If in this case, for optical filtering, we need to use a 4F system. Okay, so we're going to have a system that has a length of 4 times the focal distance of the lens. And here we have lenses, 2 lenses, each has focal distance f. Okay, and let's understand what does this system perform. So here we have a source, let's say SXY. We have a 2F system, okay, with a lens, which means here we're going to observe the Fourier transform of the source. Suppose we're putting onto this plane a mask. A simple mask. It can be an amplitude mask or both amplitude and phase mask. Let's consider for simplicity an amplitude mask. Suppose we are putting here a mask, and the mask blocks all the light that is coming through the circular region, and it's allowing all the light to pass outside the circular region. Okay, so you can simply think that there is a material here which is opaque, which is blocking light in the circular region, and there's a material outside the circular region, or maybe nothing, that allows light to pass. Okay, suppose we have such a mask here, and then we have another 2F system. Okay, and what's going to be the role of this 2F system? It's going to take another Fourier transform. Okay, so what will this system will perform at the end? So we're taking Fourier transform of the object here. Then it's passing through a mask, which means it's basically multiplied by the effect of by the mathematical expression of the mask, and then we take another Fourier transform. So the role of the mask is actually filtering. It is passing, it allows some frequencies to pass and some frequencies to be blocked. In this case, if we think about what type of filter this is this is actually a high pass filter. Okay, because we're blocking the frequencies at the center. Okay, we have an opaque object here, opaque material here, and we are allowing high frequencies to pass. So this is actually a high frequency filtering system. For example, if you're trying to make edge detection, we can use this 4F system. Okay, let's understand what we discussed in a mathematical way as well. Now we can express the mask here as a 1 times a circle function, okay, because we want this mask to be 0 inside this circle and 1 outside the circle. So this can be obtained as 1 minus a circle function. Here I'm assuming that circle function or this circular support has width has diameter of 1. Okay, and then that means in this plane, the operation we're going to have the Fourier transform of S, so capital S here, and it's going to get multiplied with this mask function H. Okay, and after passing the mask, just after the mask, the field distribution we're going to have will be UXY, okay, which is the Fourier transform of the object multiplied with this mask. Then the wave field U will transform, will observe another Fourier transform. So if you write the wave field distribution on this plane, let's call it GXY, it's going to be simply equal to the Fourier transform of UXY. So that means Fourier transform of this term. Okay, so because we here have a multiplication, that means we're going to have the Fourier transform of each term convolved. And that will be the Fourier transform of this term will be inverted S, and the Fourier transform of this will be inverted H. So we're going to basically have the inverted source convolved with the inverted H. H is the inverse Fourier transform of this mask. Okay, so the capital H is basically the frequency response of the R filter, and little h here is the impulse response of R filter. So we're applying a high pass frequency filtering in this case. Okay, and that's the mathematical justification. Okay, so this is the general idea behind optical filtering, and this had important applications. This has important applications, of course, in imaging. One application I'm going to discuss here is phase contrast microscopy. Let's understand how phase contrast microscopy works. Okay, in the phase contrast microscopy, we have a 4F system. Okay, so here you can think that this is the eye of a person looking through the microscope. Okay, and this is the microscope, the main portion of the microscope, and here you have a sample. For example, it might contain a bacteria that you wanna see. The microscope consists of basically 2 lenses and a mask. Okay, so we insert 2 lenses in a way that we form a 4F system, just like in the optical filtering setting. So from eye, okay, let's start from the object. From object to the mask, we have a 2F system. So at the mask, we have the Fourier transform of the object. The mask apply a filtering operation or apply a masking operation on the Fourier transform of the object, which corresponds to filtering. And then we have another 2F system until the light reaches our eye. And that means we're going to see the Fourier transform of the masked object, masked Fourier transform of the object, which is going to be the filtered object. Okay, thus in the phase contrast microscopy, what is specific to the phase contrast microscopy here as the mask, we use a Zernike filter, which I'm going to describe just in a few minutes. And one important thing here when we are designing the mask is our goal here is to observe or to see a transparent object. Okay, so transparent object means there is no attenuation in intensity or in amplitude. So if we look at the object with our eyes, we cannot really see this object. We cannot see transparent objects. The reason for this is our eyes only see the intensity of the objects. And if there is an object that only changes the phase, that only changes the phase of the light, we cannot see those objects. Okay, we have such transparent object here, and with this microscope, our goal is to see this transparent object. Okay, for this thing, to understand what type of mask we're going to use or the role of this mask, we should understand the mathematical model for our transparent object. So the transparent object, we said that there is no attenuation in amplitude. So if we look at the amplitude of the object, if we call the object's distribution as xy, if we look at its amplitude, we should get 1. Okay, so it's uniform everywhere in amplitude. But there's going to be change in amplitude because this object will have thicknesses which will change the phase of the light as the light passes through the object. Okay, so we write the field distribution for the object as e to the j some phase term. Okay, the phase that is due to the object, due to the thickness of the object, is called theta xy. Okay, so we basically model our transparent object as e to the j theta xy. Okay, so the amplitude is 1, but the phase is changing as a function of x and y. We're going to make one approximation here to understand the working principle of phase contrast microscopy. We're going to assume that because these objects are generally very, very thin objects with little thickness, the phase change that they're going to cause will also be small. So in the case that theta is small, we can approximate this e to the x term as 1 plus x. So 1 plus j times theta xy. So let's say our transparent object is described by this transmittance function or by this transmission function. Okay, now we're gonna choose our mask for our phase contrast microscope. We're gonna choose our mask as a Zernicke filter. You're gonna see why after we see the effect of this filter on the image. So for now, let's just understand what's a Zernicke filter. In the Zernicke filter, again, we have a circular support. So we have two different materials deposited on this mask. Outside the circular support, it's a transparent material. Okay, so its effect, it's not changing the distribution of the wave field. So it's just multiplying it with 1. And inside the circular support, we have a phase change on the field. Okay, and we're just multiplying the field with j times a. So that means we're changing the phase of the object, okay, phase of the field that is passing from the circular region by pi over 2. So this has you can think that we deposited a material here that will cause this much phase change on the wave. And let's say there is also an amplitude change by A as well. Okay, so that's our filter. So if you write our filter H, this mask operation, it's basically inside a square, inside a circular region. It is so when fx square plus fy square is less than epsilon square, so inside the circular region, the mask is equivalent to multiplying with j times a, and otherwise it's equal to 1. Okay, that's our filter model. And this is something that we can practically produce with simple materials. Okay, let's now understand what will be the role of the Zernike filter in seeing this transparent object. Okay, remember our microscope. So here, the wave that reaches the mask is the Fourier transform of the object here. So our object was this thing. So we're going to take its Fourier transform, so S f x f y, and that's going to hit the mask. That means this distribution, wavefield distribution, will be multiplied with the transmission function of the mask. Okay, and this is going to be what we will have just after the mask multiplication of these two functions. Now let's write each function. The Fourier transform of the object, transparent object, so we want to take Fourier transform of this thing. Fourier transform of 1 is going to give us an impulse at the origin in the frequency domain, and we're going to have plus j times Fourier transform of theta because of the linearity property of the Fourier transform. So we're going to have an impulse, delta fx fy, plus j times theta fx fy as the Fourier transform of the transparent object. We're going to multiply that with the mask operation. Okay, what will be that? So the impulse is gonna, let's look at each term separately. The impulse will be multiplied with this mask operation. So if you multiply the impulse with this thing, remember that impulse is staying at the origin, okay? So it is in this region. So we're gonna multiply the impulse with j times a, okay? So this is gonna be the term that we're gonna get after this multiplication. Let's look at the second term, j theta fx fy. This is a two-dimensional function, okay? And if we assume that epsilon as something very, very small, we can ignore the effect of the circular multiplication on this two-dimensional object, okay? And we can simply say that it's going to be multiplied by one almost everywhere outside this very small region. Okay, so we're going to keep that as it is after this multiplication. So this is of course an approximation, but when epsilon is very small, negligibly small, it's going to be a good approximation, good enough approximation. Okay, this is the field distribution we have just after the mask. Now, after the mask, what do we have? We have another 2F system until the light reaches our eyes. So that means the field distribution after the mask will have another Fourier transform. So we have this thing. So in our eyes, we're going to see the Fourier transform of this thing, or we can design the system in a way that it also takes inverse Fourier transform. Let's say that's an inverse Fourier transform. It's not, it will not really make a difference. Okay, let's now take the inverse Fourier transform of this field distribution after the mask, or basically the Fourier transform, inverse Fourier transform of this function. Okay, the impulse is going to be equivalent to 1 in the space domain. So we're going to get j times a from the first term, and the inverse Fourier transform of this term is going to give us j times theta xy. So that's what we're going to get into our eyes. So that's the field distribution that will hit our eyes, but not that it's in complex form, because it has both amplitude and phase. But remember that our eyes only sense intensity. So what we're going to really capture in our eyes is the intensity of IXY. Let's look at that. What is the magnitude square of IXY? So it's going to be a times theta xy magnitude square. So if you open this term, we assume a and theta. Theta is real valued already because it's a phase function. And a, we also assume that it was a real constant because it was modeling the mask as J times A. So it was just a magnification, amplitude change parameter. So if you look at this magnitude square, we are gonna basically see absolute value square is what we have, because everything inside is now real values. So we're gonna have A square times 2 times A theta xy plus theta square xy. So this is what is gonna be captured by our eyes. Okay, so depending on what is A, what we're gonna sense will change, but what is important here is now we can see the phase change of the object. So we can basically think that you can see the thickness of the object, because before it was invisible to your eyes because all the information was in the phase and we were not able to sense this phase change. But with this Zernike filter and Fourier system, we can now capture the phase of the object. For example, if A is something very small, if we choose the A parameter to be a very small amplitude change, very small amplitude transmission, in that case, when A is very small, basically this term will be dominant. Okay, we're going to just see the square of the phase of the object, okay, the phase change of the object squared in the two-dimensional space. And because the phase is generally very small, these images, so the phase contrast microscopy images that works with small A parameter will mostly look like black images, okay? There will be very small intensity values in these images. And the places that we see changes than black color will be due to the phase of or the squared phase of the object. There are also phase contrast microscopy systems that works with a large A parameter. If A is large, in that case, these two parameters will dominate the image that we see. And when A is large, we're going to see mostly large intensities. So the images will be mostly white. And but still, in that image, other than a constant DC term, we're going to see just the phase of the object. So other than the DC term, the image intensity will be proportional to the phase of the transparent object. So we will still, again, we will get information about the phase of the object. Okay, that's end of this topic. So in this lecture, we try to understand the Fourier transforming property of the lens by using a 2F system, and how this 2F system is useful for doing filtering applications in an optical way. So this is a filtering application performed using optical elements. And this type of optical filtering has many applications, and we discussed the application or the application in phase contrast microscopy that is based on Zernike filters. Okay, and with that principle, we discussed how to see transparent objects using simple lens systems. And that's all for this lecture. Stay safe. Again, we will meet with you in the next lecture.